hello. Um, in case you're new here, my name's Nathan. I am about 3/4 of a PhD. Um, Should be about, maybe 5, 6 months away from graduating, but I do know a fair bit about chemistry, and that is something I really enjoy talking about. And so, oh, thank you. That's very lovely. Yeah, so this is just a little place that we can talk about chemistry. This is kind of specifically aimed at people who are in chemistry courses, somewhere near undergrad. And so I am here to answer any questions, to talk about really anything that I feel like. And in if there's no questions or anything, I'm just going to do some chemistry stuff, chemistry problems, and explain kind of my approach to tackling these questions, and maybe just give a little bit of insight into like what's actually going on, because I think chemistry is something that lends itself very much to the use of like procedural knowledge and like using processes and step-by-step approaches to answering questions using just kind of basic fundamental knowledge, because I think that things like memorizing and shortcuts like that are not particularly useful in chemistry and in understanding what it is. So I think if you have a decent grasp of the fundamentals, I think it gets a lot easier as you go along. So with that, it is very much finals season now, and so with that, I have several students that I tutor, so this has been very busy. I've already tutored one-on-ones for 4 hours today, so I do believe this is probably going to be quite a short stream. But I will talk until my brain is fried, and yeah, then I'll stop and leave because I can. Okay. So we were working on this problem set last time. So we were just going over just kind of basic just identification of some functional groups, and then I just occasionally had a little bit of a rabbit trail, like into salicylic acid and acetylsalicylic acid, and just a bit about that. And then we talked about drawing different constitutional isomers and just rearranging the structures so as to not repeat structures and get doubles and end up with more, with you thinking you've got more than you do. And a big part of that is like numbering the atoms, because if you do that, it'll help so much to keep that straight, because it's very, very easy to get lost when all you're looking at is a bunch of lines that go off into nowhere. Alright, so let's zoom in a bit here. So, talking about building up systematic names for compounds. So I haven't actually looked all the way through this problem set, so I'm not entirely sure what is coming later. I imagine it will involve something about naming functional groups, because at the for this question, all we got is hydrocarbons, which is fine. We'll work with that. Okay, so when we're going from a structure that's given to a systematic name for the compound, the first thing to do is to to find the longest carbon chain, because everything um, everything that follows, everything that's attached to that carbon chain is based on just like that structure of the longest carbon chain, because it does not need to read left to right or right to left or whatever. It doesn't need to make any kind of spatial sense as to where this chain is going. So let's just see here. So for this one, we've got 1, 2, 3, 4, 5, 6, 7 carbons along that chain. But in order to make sure that this is actually the longest chain, we'll count the others as well. So I'm going to go 1, 2, 3, 4, 5, 6, 7, which is the same length, as you may note. So is there any other way that we could do this that would make a longer chain? 1, 2, 3, 4, 5, 6, 7. Okay, so there's 3 ways that you can make a 7-membered carbon chain out of this compound. And that's kind of a pain in the ass, because it means that we have to take these different possibilities into account when we're deciding what the longest chain is, because the next criteria that we're looking for is when we are naming the substituents, the things that branch off of the primary hydrocarbon chain. We have to try to get them to be like the lowest set of numbers possible. So let's start from here. So we'll count 1, 2, 3, 4, and then let's say 5 and 6 and 7. Okay, so if we count in this direction, then like calling this one carbon 1, this one carbon 7, then the substituents that we'll have will be located on carbon 4 and on carbon 5. But like just a cursory glance at this tells me that we should be able to do better than that. Like we should be able to get to a lower set of numbers than 4 and 5. So let's try this again. So if we go... I actually wonder. Okay, 1, 2, 3, 4. I don't want this on chisel. I want this on pen. Sorry. 5, 6, and 7. So if we number it this way, from this carbon being 1 and this one being 7, then there is only one branch off of the main chain, and it is at carbon 4. So that's still, we can still have a set of lower numbers, because the last one started at 4, but spoiler alert, we can still do better than that. But this one's kind of interesting because numbering them in this way actually cuts the number of substituents down to 1, and in this case it's just a sec butyl group that's attached at carbon 4 there. Yeah, actually want to talk a little bit about naming these hydrocarbon groups. So, let's... I'm going to do that over... No, I don't want to erase that, do I? Okay, let's just move over here a little bit. Okay. That's fine. Okay, so hydrocarbon substituents. So I'm a little bit pleased with myself because my writing with a mouse is getting quicker and more legible. Um, Although it kind of ends up looking a little bit like Comic Sans or possibly something written by a 4-year-old, but I'm pretty comfy with that for the most part. I have been doing chemistry for 12 years. I think I have yet to make a decent attempt at a hexagon. Um, I'm not an artist, and I'm very comfortable with that, and that's okay. So just know that if you can't draw worth crap, you're not alone, and it doesn't mean that you can't be good at this. Okay, so hydrocarbon substituents. What I'm meaning by this is, for example, if you've got a benzene ring, you can have substituents coming off of that benzene ring instead of just kind of the default hydrogens. You can have things like methyl groups. You can have things like ethyl groups. What was I saying about legibility? Well, never mind. Just pretend that didn't happen. You could have things like propyl groups. 2CH, 2CH3. But when you get to propyl groups, I think chains that have 3 carbons or more, there's now multiple ways that you could attach these and use them as substituents. So we have to start to subdivide the categories of these substituents. So like what I mean by this is like there's only one way to attach a methyl group, clearly, because there's only one carbon. But there's also only one way to attach an ethyl group. Because if you attach it at this carbon instead, well, this carbon would be the one with CH2 because it's in the middle, and this one would end up with CH3. So there's no difference between those whatsoever. But because it would be just attached to a CH2 and then a CH3, and that is an ethyl group. So when we get to propyl, we have to start being specific about how this is attached. So this is an N-propyl. And what that means is it's, whoops, that's too many lines. Okay, so 3 carbons. Let's actually draw this out just because. So let's say whatever you're attaching it to, let's just call it R. And so if you attach the propyl group in just a straight chain, so just 1, 2, 3 all in a row, that is an N-propyl group. The N, I believe, is it stands for normal. I'm not entirely sure of that, but I think that's what it is. Nobody really cares. It's just N-propyl. Means it's a straight chain. But you can also have a group like this. So this is also a 3-carbon chain. But in this instance, it is connected at the middle carbon, and that is distinct from attaching it as a chain, as an N-propyl group. And this is called I-propyl, or otherwise isopropyl. And that may sound familiar from things like isopropyl alcohol, where there is a hydroxyl group attached at the middle carbon of a propane chain. And so that is why it is so named. Excuse me. So, when we get to higher chains, things like butyl groups, we've got N-butyl, which is just a straight chain of butane. and so just connect it to the R 1, 2, 3, 4 in a row. Oh, very quickly, one thing you may notice is in this propyl group there are 7 hydrogens, 2, 2, and 3. And this is absolutely and necessarily also true of an isopropyl group, where we have 1, 3, and 3. There's also 7 hydrogens, so there's no difference there between the number of hydrogens. They're just rearranged, which is another way actually that you can tell that this is distinct, because the connectivity of the group is different in isopropyl versus N-propyl. Okay, so we've got N-butyl. We've also got isobutyl. And this is a chain that looks like this. That's not a hydrogen. God, I promise I'm really, really good at this stuff, guys. Okay, try it again. That's a carbon. That's a carbon. Okay, so yeah, this is an isobutyl group where instead of just a straight chain, we've got 2 in a row, and then it branches into 2 methyl groups. So these would end up as methyl groups. This would have 1 hydrogen, and this would have 2 hydrogens. The other way that you can think about this is if these are carbons 1, 2, 3, and 4, you could think of this as carbon 4 being moved and attached to carbon 2. And that's a perfectly valid way to think about this. Just changing the connectivity by moving this terminal carbon over to, like, just leapfrogging over carbon 3 there. So this would be 1, 2, 3, and 4. And just like creating a new isomer of this, which is terribly familiar to what we did last time with drawing constitutional isomers, where we just took the terminal carbon and move it to 2 carbons over. So same way of generating isomers, which is why I do it like that. It's nice and systematic, and we like it. Okay, so, but we don't stop there, because there's more to do. Because we have got things like S-butyl. N for normal, question mark. Very good. S is for sec-butyl, or more properly, secondary butyl. And what this looks like is, I'm going to maybe, sorry, yeah. Okay, that's a very bad picture of what what a sec-butyl group looks like. Let's clear that up. Okay, I've got a way to do this. So, okay. All right. So this is what a sec-butyl group looks like. So it's whatever you're connecting it to is connected to the second one, the second carbon of this 4-carbon chain, and then there's 1 carbon off to one side and a 2-carbon chain off to the other side. So a way to think about this one is, if you take the R group instead of one of the carbons, and you move that over to carbon 2. This is a bad example because that's not what that one looks like. So, okay, so take the R group and move that over to carbon 2 instead of moving all this stuff around. And that leads to this thing. I'm just trying to think if I have anything else to say about that. I kind of think I don't. That's just how you make a secondary butyl group. The last way that you can arrange a butyl group is by, excuse you, is by making it into a T-butyl group. And the T stands for tertiary. Okay. And what this looks like is something very much like this, where you have, whoops, 3 methyl groups coming off of that central carbon. And yeah, so in all of these cases, it's a C4H9 is just the formula for a butyl group, and these are all the ways that you can arrange that. And T-butyl groups are great for making things like really bulky bases, like potassium terbutoxide. Yeah, so you see, sometimes it's called T-butyl, sometimes it's called tert-butyl, just like S-butyl, sometimes called sec-butyl, because we get lazy and we don't like to pronounce the whole thing. All right, so anyways, that's probably all I'll go over right now, because like this it does get a little messy in a hurry, because you start with nothing until you get to propyl, then you've got 2 variants, and then in butyl you've got 4 variants, and in a pentyl group, I'm not sure, probably like 6. The only one I know off the top of my head is a neopentyl group, but I'm not going to explain that because I don't feel like it. Not likely to come up. We'll put it that way. It's in all the years that I've been studying this, the only time I've come across a neopentyl group was in taking an OChem class. So, all right. So this is another way that we could name this group. It would honestly be fine to name it like this. You could name it systematically like this and come out to the same structure every time. But because IUPAC does not they only want one answer for everything. They don't want multiple ways to do things. So there's other rules that we have to follow, and I have to take just one moment and say thank you for the follow. I hope I'm saying your name right, Leasty. It's lovely to see you here. Just in case you probably didn't catch my spiel because this is Twitch and it's all live. So hello, my name's Nathan. I am a PhD student, pretty close to the end of my degree, and I like chemistry because I'm a great big nerd. So I really like talking about this stuff. If you've got any questions at all, any topics you want to talk about, or just like general sciencey stuff, I am always here for that. Otherwise, I'm just going to keep working through the problems, and we'll work on that for a bit. Okay, so for naming this one, that's not going to be the correctest way to do it. So what we do instead is, if we start numbering from here, we go 1, 2, 3, 4, 5, 6, and 7. So if we number it this way, now our substituents begin at carbon number 3. So this reduces the this reduces the substituent numbers that we assign when we're going through and naming this stuff. So we will stick with this for now. So now we've decided on what is our longest carbon chain, and we've decided how we're going to number these carbons. So now we need to figure out the identity of the substituents, and then we can construct the full name. So here on carbon 3, that's just a methyl group, and then on carbon 4, well, just a second, I'll take a moment and say that is a methyl group. Now on carbon 4, we've got 1, 2, 3, a propyl group. And if you'll recall from me talking at you for a while, a propyl group that is just a straight unbranched chain is an N-propyl group. So we do have to be specific about the types of group we're talking about. And yeah, if you're ever wondering if it's specific or not, then like once you've figured out once you've got your guess or what you have answer for the name of the compound, if you're not sure and you're not in an exam and you have time, try to draw the molecule using nothing but the name that you've written down. And if you find you can't do that, your name is probably wrong, because it's like it should be like every name should refer to exactly one possible structure and no more. Okay, so we've got a 3-methyl and 4 N-propyl. And that is going to be the lowest set of numbers that we can assign to this molecule and to these groups. Because if we were counting from the other end, like if we called this 1 and this 7, we would have 4 and 5 as our substituent numbers, and 3 and 4 is lower, so we go with that. So, then when we're building up the name, start with the carbon chain. So it is a 7-carbon chain, and so we go methyl, or meth, eth, prop, bute, pent, hex, hept. So this is going to be a hept group. It is all saturated, which is to say that all of these are carbon-carbon single bonds. And so that means that is going to be a heptane. And that just stems from, I'll really quickly go over and explain. All saturated, all single bonds is an alkane. If you've got something like this, and you've got a double bond between two of the carbons, that is an alkene. And if you've got, let's make that less ugly. If you've got a carbon-carbon triple bond, then that makes it an alkyne. So, in the order of these saturations is fully saturated, alkane, double bond, alkene, triple bond, alkyne. Canes, kenes, kynes. If you can keep those straight, you can name 80% of things in organic chemistry. Okay, so again, these are all single bonds, so this is a heptane. But now we've got, so we got to move this a little bit. We've got a 3-methyl, and we've got a 4N-propyl. So when we are naming those groups and like putting them in order in the name, we don't put them in order by the substituent number. We put them alphabetically by the substituent name. And the N here does not count. We don't name it based on N. We name it based on the P for propyl. And for the methyl group, we do that it's in M for methyl. So M comes before P, so we're going to do just 3-methyl, and then I'm going to put dash in there, and 4N. I'm going to run out of room. Why do I always do this to myself? Okay. So one thing this whiteboard does not really... Well, maybe it does. Can I just move... No, I just want to move this. Dear God. Okay, so I'm going to have to play with that later and see what on earth that does. But right now, I have been silly, and I need to make this bigger. Okay. 3-methyl dash 4N propyl heptane. Okay, so that is looking a little small on my screen, so I'm going to zoom in on that. So yeah, dashes between numbers and letters, and dashes around the designation of these chain substituents. So like for the N-propyl, it's 4-N-propyl. And so on and so forth. Okay. So that's it. 3-methyl, 4N-propyl heptane. And we're done 1. Okay. So for this one. Now the longest carbon chain on this one is going to be real easy to find, actually. So I'm going to start from this one. We'll go 1, 2, 3, 4, 5, and 6. Okay. So with a primary chain of 6 carbons, we know that's going to be a hex. They are all single bonds. There's no double bonds, no unsaturations in here, so it's going to be a hexane. Now we need to locate and identify the substituents. So everything that's not the main carbon chain is here. So it's 2 there. So there's 2 methyl groups. There's 3 methyl groups. 2 of them on carbon 2 and 1 of them on carbon 5. So the way that we are going to name that is we're going to go 2, 2, 5 dash trimethyl hexane. And so when we're naming substituents, and especially like multiple substituents coming from the same carbon, you must repeat the number of the carbon as many times as you need to for the substituents that are on it. So in this case, there's 2 methyl groups on 2, so we have to put 2 twice. It is not enough to say 2-dimethyl 5-methyl hexane. You could draw this molecule based on that, but it's a little clunky. It's longer than it needs to be, and it's simply not correct by international convention. So, and so when they're all the same substituent, all 3 of these are methyl groups. We group them all together into one term here, and then we put a prefix on before the methyl group that says how many we're talking about. So this is going to be 2, 2, 5 tri, because there's 3 methyl hexane. It doesn't make any difference for this molecule, but in other cases where you have like let's say you had a chlorine on this. Actually, let's make it something more like God, why can't I think of functional groups? Don't worry about it. It's fine. Put it as chlorine. So this would be 4 chloro dash 2,2,5 dash trimethylhexane. I didn't make the point that I was hoping to make because my brain isn't working and I can't think of any functional groups that would throw off the alphabetization. Because remember, we do not order the name by the substituent number. We order it by the alphabetical name of the substituent. So in this case, the 4-chloro comes before the 2,2,5-trimethyl because C comes before M, not T. Because like the same way that we don't use the N in N-propyl to determine the alphabetical order, and we don't use prefixes like dimethyl, trimethyl, tetramethyl, whatever. So we never use the prefix. We always use the first letter of the of the functional group name, or the substituent name rather. Okay. All right. So, moving on from that. I'm going to do this one because I feel like it and there's more room down here. So, once again, we're going to find the longest carbon chain, which is going to be the primary carbon chain. So we go 1, 2, 3, 4, 5, 6. That would have grown 6. Okay, there we go. It's a little better. So 6, and from here, there's either direction we go, there's 2 more carbons, so it doesn't really matter. I'm actually not sure that's true. No, it's not true. Okay. All right, so we're going to go this way. 7 here and 8 here. So the reason that we do that, am I going to second guess myself? Maybe 2, 3, 6. Yeah. Okay. Yeah. This is the better way to do it. Because you'll end up with the lowest set of numbers possible. You can always try these things on your own and see if you can get a better answer. And if you do, I'd love to know. But in this case, this is going to give us the lowest set of substituent numbers. So we'll go from here. We'll play with it anyways. Okay, so it is an 8-carbon chain primarily, so we start with oct. And these are all single bonds, it's fully saturated, so it is going to be an octane. Now, identifying substituents. So we've got a methyl group, another methyl group, another methyl group, an ethyl group, and an isopropyl group. So, what this is going to be is, so let's think about alphabetization. So this is going to be, let's just draw all our puzzle pieces up here. So we're going to have 6 ethyl. We're going to have 5 isopropyl. And for this, you can put I-propyl, like I-propyl, or you can just use isopropyl. Either of those would be perfectly fine. It's referring to the same thing. And we've got 2, 2, 7 trimethyl. Dip. Okay, so not only did I say methyl or something, like I'm just, like I half said it in a British way, but I also misspelled it. I'm doing so good. It's a good thing I've studied this for 12 goddamn years. I'm so good. Okay, all right. So we got 2,2,7 trimethyl, 6 ethyl, 5 isopropyl. God, there's absolutely part of me that really wants to rearrange this and see if we can get any lower numbers. Just trying to think, because this would be 2-methyl, 3-ethyl, 4-isopropyl, then 7,7-trimethyl. Nope, so 2 and 2 and 5, 6, 7 is still the best option that I see. So we'll go with that. Okay, so now alphabetically. I'm actually going to move this so I can show you the full name, because that's what a good streamer would do. Okay, so we've got, so alphabetically, the ethyl is going to come first, then the methyl, and then the propyl. So we're going to say, if we can actually manage to write worth of crap, 6-ethyl dash 2,2,7 trimethyl 5-isopropyl octane. Ha! Fits perfectly, like I planned it that way. Okay, all right, fine. I won't pretend that I did that on purpose. Nobody would believe me. Okay, well, as I believe I have been showing, my brain isn't working great today. I've done a lot of tutoring already today, and I think I'm almost as fried as my students were today. Luckily, I don't have any finals to do. Okay, so there's a little short stream for you. Yeah, hope you enjoyed. Hope you have a lovely day. Bye.